physics that is totally different from everything you guys have seen so far, right? Like solving particle physics problem. Yeah, 相似 is more of a condensed matter relative things. Oh, Zhong okay, ask him to give. Yeah, can do that. He's teaching. He's not teaching you guys, right? He's teaching your junior batch right now, electromagnetism. So yeah, can consider. He's teaching you guys lab. Oh, okay. Yeah, particle physics is another huge subject. There's a just like black hole. There's like a big experimental side, and then there's a big theoretical side. The theoretical physicists don't know what the experiments people are doing, and because there's a lot of problems to solve in the experimental side, so it became a huge research subject, right? So okay, let me ask Chong later, or you guys can ask him also, since he teaches you guys lab, right? But for us today, let us continue. We are continuing chapter 3, right? So we have moved on to chapter 3 already. We will start to talk about one-dimensional potentials. So I guess there might be a source of confusion here. When I say one dimension here, right, it just means that it's like a Newton one dimension. We are focusing on the x direction, and we do not refer to the dimension of Hilbert space because that will be infinite. So in order to understand how to solve Schrödinger equation for the x coordinates, we need to understand an infinite dimensional Hilbert space. Okay, but it sounds scary, infinite dimensional, but actually you guys have done this before already in the modern physics. So we're going to do this again, right? So, but before we do that, let me remind you a few things about the recap a few things about discrete Hilbert space, right? So let's recap discrete Hilbert space first, so that it's not so scary to suddenly jump into infinite dimensional. So discrete Hilbert space of finite dimension, right? So what am I talking about? So let's recap a few facts first. For hopefully it is very familiar to everyone by now. We have been talking about particles of spin up and then with particles of spin down. So these are discrete states, right? And then we describe an arbitrary state by C1 and then spin up, and then C2 spin down, and we represent this as a column vector. So C1 and C2. So that means the dimension of Hilbert space here, I have two linearly independent bases. So the dimension here is 2, right? And then what else did we have? We had the completeness relation, right? So we had completeness relation, which is to say that if I do the ket bra, right, and then for up up and down down, is you will get the identity matrix, right? And I'll just write this, right? So completeness relation is given by this, and then an arbitrary state. Actually, I already written here, which is just C1 spin up plus C2 spin down. But what I do want to point out is that the C1 is given by computing up, and then you close with the ket, the state itself. And then to calculate C2, usually you don't know, you just like know this kind of state. So to calculate C2, hang on, did I record? Yes, I am. Oh, so Chong worked on particle physics experiment before. That's interesting. So Jia Cheng should be familiar with this chapter very well, right? The stuff about potential wells. Where was I? Okay. To calculate C2, and then you close with the state. Okay. So this part is pretty easy, and then the orthonormality condition is spin up with spin up is 1, right? And spin down with spin down is also 1. and if you take any different spin, the inner product is going to be 0, right? So this is where the dimension is equals to 2, right? So if the dimension, we can generalize this to any arbitrary but finite dimension, everything is still the same, right? So even though we spend a lot of time doing two-level system, 2 dimensions, but if it's 3, 4, or 5, shouldn't be a problem, right? So I'm going to just write E1, E2 in general until En. They are discrete states, right? So the completeness relation is going to be the completeness relation is going to be the, well, it's not just 2 terms now, but I need to sum from 1 to n, right? Ej and then Ej, and then it's going to get an identity matrix, right? The rest are all 0, but it's still the identity matrix of size n, okay? So no problem there. And then an arbitrary state is given by, well, it is a combination or generally sum from 1 to n of the coefficient and then Ej, okay? So you can write this as a column vector, C1, C2, until Cn, right? And then in order to compute the Cn, or any Cj is equals to, you take the basis Ej and then you close with the state, right? You do the bra-ket. And then of course the orthonormality is given by, well, if I take any basis Ei and then take some other basis Ej, could be anything, and then it's called delta Ij. It is our Kronecker delta, right? So it's 1 if I equals to j and 0 for other values when they are not equal to j. So this is the Kronecker delta, right? So everything here is just a recap of when your Hilbert space is having a finite dimensions. So now let us go to infinite dimensional Hilbert space, because what we are going to talk about, right? Well, let us forget about the language of infinite or finite or infinite, but basically in physics what we want to measure is position, right? So every time since mechanics, since Newton's law, we are always interested in position, well, and also momentum. So these are your 2 important concepts in physics, right? And therefore they are observables. Okay, so they are observables. So that means by the postulate of quantum mechanics, we should have a Hermitian operator associated to it. Okay, these are observables, and then, but here is the problem, right? But its value can take any continuous value. Right? In other words, it can take any real number. Okay, it's not just 2 values, but it can be any number. So that means this is it is a continuous variable. So this is the problem that we want to address. How do we consider a state? Because we are still following the postulates of quantum mechanics, right? The state should be something in Hilbert space, and the state is supposed to list down all the possible values the particle can occupy. If we are talking about spin, it can either be up or down, right? So these are all the possible values, but for position, it could be anywhere, right? It could be here, 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 here. So if I literally want to write everything out, it would be impossible, because let's say the particle is at position 0, or a particle at 2 meters from the origin, or 2.5, or 2.55, or 2.501, right? It could be anything. So it's like an infinite list of columns, right? So the possible values x1, x2 is an infinite list of columns. That is why we have an infinite dimensional Hilbert space. So there are infinitely many possible positions for a particle. So if you are still following the postulates, well, all these states are states, right? A particle is a quantum state, and it should occupy a Hilbert space. So therefore, the dimension of my Hilbert space is infinity. So this is the problem that we want to deal with for today. Okay, so this is the issue. So now how do we handle this? So we try to do it carefully, one by one. So let's start with position. Okay, so this is the first section. How do we deal with position? Okay, so let us like write everything down from the beginning of what we know very carefully. Like I said, it is an observable, right? So it is an observable. So for instance, just to make it more clear, right, we say that the position of an electron is at some position x equals to 0.5 from some reference point, so from the origin. Okay, so yeah, depends on where you set your origin. And by the postulates of quantum mechanics, your result of your measurement is an eigenvalue of an Hermitian operator, right? So if you guys are still confused of what does it mean by the eigenvalue of an operator, right, it's like statements like this: it is an eigenvalue. Okay, that means this number should play the role of an eigenvalue, right? It is only one possible eigenvalue, right? 0.5. If I another electron at a different place, I get a different eigenvalue. Okay, so this is just to reiterate what we have been stressing all the way since the first lecture, is to say that it is an observable, so there should be an Hermitian operator. Right, that is associated to what you are measuring, and what you are measuring now is a position. So position, right? So I will call this Hermitian operator X. Okay, some textbook they put a little hat above it just to tell you it's an operator, but I don't think we need, right? So, and then it's going to have some eigenstates. Okay, and by postulates of quantum mechanics, there should exist some eigenstate that after you operate on it, you will still be the same state, but you get an eigenvalue, right? So to emphasize, this is an operator, and this is the eigenvalue, and therefore this is the eigenstate. Okay, so it should have something like this form. Okay, so, and of course, like I said, right, there are infinitely many possible eigenstates, right? Because since x can be any real number, right, there are infinitely many eigenstates, right? So x, right, because this x can be from any number, 0.1, 0.001, negative numbers, all the way. Okay, so how do we like describe states in this basis? Because remember what we have been doing. Once we got an operator, we find the eigenstates, and then once we got eigenstates, we got the eigenvalue, and then also we can use the eigenstate as a basis for my Hilbert states, right? So like we did before, previously, right? We are going to use the eigenstates as a basis of the Hilbert space. Okay, so this is what we shall try to do. But now, how do you express something with an infinite basis? Yes, eigenvalue can be real number, because position is a real number, right? And also it's a Hermitian operator, therefore we must have real numbers. Okay, so yeah, so what we did last time was we can express a state in this basis. So a state can be expanded in a basis as how did we did last time, right? So how did we did last time is well, a particular state is going to be having some coefficient and then times the basis, right? So, and then we sum over. Okay, so remember we did something like this, right? So for a discrete set of states, this is what we did, right? So we are summing over a coefficient times the basis. This is for the finite dimension, right? So we sum from 1 to n. So we want to try to do something similar to a continuous basis as well. So my basis is going to be x, right? And then the coefficient is going to be some coefficient that will be dependent on x, right? So the basis ej will be attached to some coefficient cj. So the basis of some x will be attached to some function x. And then because it is continuous, right, it's not enough to just sum over, but what we are doing is we are integrating. Okay, so we do something like this. So a state can be expressed in this form. Okay, so just to compare and contrast, I should probably write down for the discrete, right? So discrete basis is it was a summation of I, and then I got Cj and then Ej. Okay, so just to compare and contrast, this summation becomes this, the coefficient becomes this, and then the basis becomes this. Okay, so when it's finite n from 1 to n, you do this, but if it's a continuous basis, then summation becomes a integration. Okay, so I'm doing this very slowly and very carefully is because for those who did modern physics, you did the wave function of position. This is the one. This is the thing over here. And now we realize that it is kind of like a generalization of the coefficient C1, C2 that we did in the previous chapter. Okay? So, yeah. Okay? So just to, so I should maybe write some more details about it. I should say that where this one is a function of x. Okay, it's a function of x, right? So therefore, given a state psi, then we can obtain psi x by doing we close this with the basis. So this will give me psi x. Right? Remember last time, compare and contrast what we did this. Given psi, we obtain Cj by doing Ej psi. Right? So we compare and contrast these two cases that we're happening here. Okay, so I'm trying to convince you guys that even though it's infinite dimensional, everything is still the same. We just need to change summation into integration. And then these are a finite list of numbers, but finite list of numbers generalized into continuous, it becomes a function of x, right? So if for any x I get a different value, this one for j equals to 1, 2, 3, 4, I get different values. Same story, but for x from 0 to infinity, I get different values of the function. Okay, so these are this is our, well, this is your introduction to continuous basis. Actually, interesting to say this, Kahing, but I don't think we'll see balls or tubes here, at least not yet, right? Not for now. We will see a square later when we talk about the potential well. So psi x, not yet. Psi x means, so psi x is like the coefficient. So just to remember, right, when we were talking about an arbitrary state, we have a basis. So how do we write down a vector? So a vector means it's a sum of coefficient times basis, right? Even for normal vectors, right? So last time we were like a velocity vector, right? So velocity vector is vxi plus vyj right? So these are the coefficient, and then this is the basis, okay? And then when we are doing a two-level system, this is the coefficient and this is the basis. So now here the psi x is, for every x, I have the coefficient of this x, okay? So it is the coefficient and the basis. Is that clear? So yeah, Kaishan, you can say that. So if the state is like it becomes a continuous, right? So we got, because it's expressed in this. So now we cannot imagine a three-dimensional or two-dimensional vector space anymore. So we cannot imagine this as a vector anymore, right? Because our basis is infinite. We can only imagine at most a three-dimensional object, right, using our imaginations. But now the dimension is infinite, so we shouldn't even imagine this. But what we can do is, this is a function. We have learned function since calculus 1. We can manipulate this function. We can even imagine this function, and that is what we shall do. Okay, so this is like kind of like switching our mode of thinking a little bit. When we are doing this, yeah, we can draw a vector space and things like that. But now we just stop thinking about vector space just temporarily, because now these are functions. Okay. Yeah, so in simple terms, also because it's continuous, we will be doing integrations a lot, right? And that is also why we are not doing that is why I was saying we won't see balls or tubes, because we are not doing the we are not using integration for geometry, right? We are doing the integration because it is a continuous basis. So there's not really a need to talk about balls and cylinders and things like that. Not like what we did for our previous courses, right? Okay, so yeah, now we have this as a basis. If you still want to think of this as a Hilbert space, then yeah, we can say I can just like try to list down a few numbers, but you can quickly see it's going to be impossible, right? 0.000125 So you see there's infinitely many numbers I can write, so it's impossible, right? So we can say that an arbitrary state is like, to answer Zuri's question also, it's a summation of the coefficients, right? So my coefficient is the psi. So when x is equal to 0.01, it is the coefficient of 0.01 basis. If my x is 0.02, then that means I calculate the value of the function at 0.02. It will be some number, right? And then I got 0.02. And then see, it's like, yeah, it's impossible to write everything for a 0.01253. At least make some effort to try at least, right? So I sum over infinitely many numbers, and this is why I can't, but I can integrate, right? So it's like, yeah, Riemann sum, kind of like doing a Riemann sum. Okay, well, in any case, right, these are eigenstates of x, so they should be orthogonal. Okay, so here comes the question: how do we express the orthogonality or orthonormality of the basis? Right, so they form a basis. So I was saying that they form a basis, right? So how do we say something that is orthogonal? We can carry over some concepts. So a basis, right, from mechanics, basis I, basis j. So I times j, I inner product with j will get 0, right? Perpendicular axis, you get 0 vectors. Parallel vector is, for discrete, you get 1, okay? So I'm just gonna write it out first, and then I will slowly explain. So the orthonormality of continuous basis is given by, okay, so usually I take inner product between two vectors, right? So I take one vector and then one basis vector, and then I times with another basis vector. Okay, so this is the orthonormality we want to check. When they are not the same, they should give you 0. So this is the main point here. Okay, so this is like the yeah, I'm laughing now because it is a very unique thing for physics. So it doesn't matter. Yeah, it's just for convenience. It makes no difference. Okay, so with respect to dx. Yeah, but so if Gloria is still here, she will know lah, because I was telling this, like, in physics it is usually convenient to write the dx in front rather than at the back. It's just for convenience purposes. It's the same, yeah. So yeah, it's not a different thing, it's the same, no special meaning, it's for convenience. And sometimes even in normal calculus, right, you will see, you know, I would probably do something like this, right? So x squared is equals to 1 over 3 x cubed plus c. It's just a convenient way to do things. And when you do multivariable calculus, it's actually more easier to put your dx in front. Okay, so yeah, in this chapter, my dx is almost always in the front. So, but back to this problem, how do we express the orthonormality condition? Well, I'll just tell you the answer, because there's a lot of math concept you haven't learned yet. So I'm telling you right now, right? So this, you probably haven't seen this before. I will write this notation, because for the discrete, for the finite case, right, we did this, right? Ei Ej is equals to delta Ij. So so this one is for the continuous version of it. So what does this mean? Okay, so this one is totally new to you guys, I think, even new to math people as well, right? I don't know if you learned this in your math course, but this thing here is what we call the delta function. Okay, so Dirac delta function, and it is defined by the following. Okay, so it is defined by there's a few ways to write this. Okay, so it is, let me write it like this. So x prime minus x. So it depends on what is the value of x and what is the value of x prime. So to start with something familiar, you can say that it is equal to the integral of the exponential I k x minus x, and then integrate this with respect to dx. Okay, so it is not the official definition from math, but it helps to just imagine that this is actually the solution for this integration. Okay, so I encourage you to try this integration yourself. If you work out this integration, right, you will get 0 if x prime is not equals to x, and it's actually infinity if x prime is equals to x. Right, so if x prime equals to x is 0, so you integrate, you just get infinity. Right? So this is my this is the Dirac delta function. So if you plot the graph of a Dirac delta function, right? Let's say I plot against my x-axis, and then this is the value of my function. So it is 0 for any value that is not equals to x prime. Okay, so that means if it's not equals to x prime is some fixed number. You can just imagine it's 5 or something. Okay, so is 0, and then it's infinity only when here. So it's like there's a spike, suddenly jump to infinity, but after that back to 0. Okay, So this is the delta function. And why do we want to define it to be infinity? Well, one of the important properties of the delta function is the area under the delta function is equals to 0. So delta x prime minus x, this time I write my dx is here. The area under this is 1, right? So you can imagine the width of the curve is very small, but the height of the graph is very high, such that the area under the graph is just exactly equals to 1. Okay, so this is the Dirac delta function. Yeah, but don't worry lah. Not in this course, not so long. Yeah, but in like for future research kind of thing, then yes. Oh, okay. So Tao Shen got use it. Oh, then okay, good. No, x prime is not conjugate. It just means x1, x2. Yeah. Oh yeah. Yeah, I remember which equation we were talking about. It's like few lines long, like what the left hand side equals to something, and then equals to something, and then something, and then something, and something. Like that. So yeah, for certain areas of physics you need to do this. So okay, so I guess since Tao Shen mentioned it before, so it's not super alien to everyone, I guess. Another property, even if you know or you don't know, I will remind you here that the area under the graph, if I multiply this with another function, right, and then if I integrate with respect to dx, because right, this is like a very magic function, because this is 0 everywhere else, so if you times this, then it will make the function 0 everywhere else. And then the area is in such a way that when you calculate this and you integrate, right, the answer is exactly equals to the value of that function at the spike. The value of f at the spike. Okay, so I always call this the spike. It's not a common word that textbooks say, but it is a spike, right? It's suddenly pum, like this. So the delta function is somehow is a machine that function is a whole function, right? For x, any number, there's a different value. But if I just want to know what is the value of the function here at the spike, so I just put the spike there, and then it will tell me what is the number of that function. Okay, I should show you an example. This is page 3. Okay, this is page 4. Okay, so let's take an example, right? Example. So let's say my function, let's say I'm given a function x squared plus 1, right? And then let's say I take x prime. It's not a complex conjugate, it's just some other value of x. So let's say this value of x is equals to 5. Okay, so then it turns out that using the property, right, the integral of my function of delta of 5 minus x, and then times my function fx, integrate this with respect to dx is, well, this is my delta function, 5 minus x, right? And then my function here is x squared plus 1, and then I integrate this with respect to dx. Okay, fine, my dx is at the back. Okay, and my spike is at x equals to 5, so my spike is at 5, and this will tell me the answer at 5 squared plus 1, right, which is 26. Okay, so just to reiterate, right, the integral delta x prime minus x fx with respect to dx picks out the value of the function at x at the spike, or I should say at the spike. x equals to x prime. Okay, is it clear yet? Okay. So let me ask you this question, right? Okay, so what if I integrate, so this is integral from negative infinity to infinity. The spike is at 5. So if I integrate from 6 to infinity, what answer do you get? Right, so I integrate my delta function 5 minus x, and then my function f of x. Right, so if I integrate this, what do I get? The answer is 0. Okay, because look at this domain, right? So for this, right, my delta 5 minus x is 0 in this domain. Right? So because I integrate from 6 onwards, so there's nothing here. Right? So the answer is going to be 0. Integral, yeah. But no lah, like I said, it depends on which area you're working on. Well, it's not yet a Gaussian. We will deal with a Gaussian later. Good question, Jia Sheng. So I don't want to answer 5 first. Let's say 4. Okay. So let's say 4 first. So I will integrate 5 to x, fx dx, and then the answer is going to be f of 5. Right? And the reason is because this domain contains the spike. Contains the spike. Okay. Yeah, so correct. So spoiler, got the answer already. 5 to infinity of my delta function 5 to x, fx is equals to, is it? I think it's half. I'm if I remember correctly. Yeah, but the reason is this is tricky because this needs to be proven. Properly. Okay, so this is a bit more tricky, right? But I will leave this to the math side. We won't be dealing with this quite often. Okay, so we will, like for us, right, we are just trying to learn this for the first time. So we're taking the baby steps. So we just do the simple case first. But this is definitely an easy problem. I can't remember this formula, but definitely this one I remember is like from 5 to infinity of the delta function alone, the area is half. Okay, so this one I know, this one I remember, but whether it's half of this, I think it is. I can't remember exactly. I can't remember because we won't be using this much in this chapter. Okay, so that is the that was the delta function, right? So why did we do this? Remember, we are talking about the orthonormality of two states. So for some x inner product with some other number of x, either it's 5 or 5 and 5.2 or something like that, it is given by the delta function. Right, so this is the main point that we want to learn here because of we are learning the Dirac delta function because of this thing, because we want to express something using orthonormality. Right, so yeah, like I said, it's like yeah, correct. So you should have bet money before I tell you the answer, right? No, actually I'm not sure, but it's something that can be checked in the math textbook. In math, I think you learn this in mathematical analysis 1 or 2, I think. So one of the advanced courses, but we need to use this now because we need to deal with the position eigenstates. Okay, so now I hope everyone is okay with the delta function, right? It's a new concept, right? It's like I said, in year 2 in this course, you are learning a lot of new concept, not like last year, right? Last year, a lot of concept you learned before in high school, you're just learning it again. Here is like a lot of new stuff, so we need to like make sure we understand everything carefully. So, but the thing about this, right, like I said, it's a magic function. It just picks out the value of the function at the spike, right? If you just do it with some other function. Okay, so I will show you how it works now. We just need to introduce one more thing. Okay, the thing I want to another thing is, well, we introduce the basis expansion, right? It's an eigenstate. The x is an eigenstate, but how about completeness? Right? So how about the completeness of these states x? Previously for discrete, right? For the EJ, right? The completeness relation is the sum of the ket bra EJ. Okay? So then the completeness here is going to be the same story. Instead of sum, so it's still the ket bra. So x, the ket bra of the same basis, right? But I need to sum over everything in order to get me a identity operator. Okay, so identity operator, and like, yeah, you guys know already, integration change to summation, right? And usually I seldom write the limits of integration because I'm lazy and it wastes too much time, but usually it means from negative infinity to positive infinity. Okay, so this is an identity operator, but we are talking about infinite dimensional basis. So this is an identity for an infinite matrix. Yeah, so it's an identity for infinite matrix. Okay, but even writing a matrix also, I shouldn't write because it looks like it's a discrete number, but this one is continuous. So I'm just telling you, but we shouldn't imagine this. But the identity operator is easy to imagine, right? 1 times anything, you get back the same thing. Okay. So how do we use this? Well, now let us play around with this thing, and then what was it? The completeness relation and the wave function. Okay. So like any state can for any state. Okay. So let's start with some any state psi. Okay. Well, psi, I can, for no reason, psi is of course 1 times psi, right? It's the identity operator, right? So I can do this for no reason, and 1 is also equals to this. So therefore this is a very common trick when dealing with bra-ket. So psi is actually the same as dx, and then the ket bra x, and then close with psi. Okay. And what was this? So this one was what I define as my wave function, right? So this is my psi x. This is my what I call the position wave function. Right? So from here I have recovered what I said just now, that the wave function is sum over the coefficient. We no longer say that this is the coefficient, but it's the psi x, and then multiplied by the basis. Okay, so yeah, so you got something like this. Let me use the capital letter psi. Okay. Oh yeah, orthogonal means perpendicular. Yeah, remember. Yeah, I think we forgot already because I mentioned this a long time ago in the first lecture, lecture 1. Orthogonal means perpendicular. Yes, exactly. This is what we want to do. Yes. Yeah. So that is why, yeah, that's why we call it the orthogonality relation. orthogonality is a fancy word for perpendicular. So yeah, so before we become too fancy, we must remember our like simple words lah. So orthogonality is just a fancy perpendicular, right? So perpendicular means the perpendicular basis, right? Like ij, right? When I and j are two different bases, so different bases dot product you get 0, but I dot I is 1, j dot j is 1. So it's a generalization of this, right? So yeah, I dot I is 1, j dot j is 1, I dot j is 0. Okay, so this one was from mechanics, right? And then previous chapter we do this same story. Up is 1, down is 1, but up down or down up is 0. Okay, but now we generalize to this situation. Okay. Oh yeah, so we must remember the x values are now what we call the basis. Okay, this is Hilbert space. This is not the R3 or R2, right? It's a Hilbert space. Okay, so it takes a while to get used to it. I know it's new for now, but I think, you know, once we work out a few problems over the next few weeks, you start to get used to it, right? It's just something that is new, so just practice and get used to it. I got a cat here. So what else do we need what concept do we need to carry over? What we did last time was we did the Hermitian conjugate, right? That is a fancy word that to say that do the dagger, right? So that means you want to get the bra, right? So the bra of this is just taking the dagger, right? So how do you dagger this? It's very simple. The integral is still the same. You still need to integrate. But dagger, remember, all the number change to the complex conjugate, right? So this function is a function that might have complex number inside. So you just complex conjugate everyone. And then you just dagger this, so it becomes a bra. Okay? Yes, right? So this is why we got infinitely many bases. So put x into a basis. Every x becomes a basis. So this is a good gift to use here. It is like a different way to look at things, right? So in mechanics, you look at x as one direction with a basis I. But now every I itself is a element of a Hilbert space that is infinite dimensional. So it is a bit of a mind-bending way to think about things if you're not used to it, right? But like I said, if imagining basis is a bit uncomfortable, then just remember these are just functions. Okay, so we just deal with them as functions. In any case, what we should do is, I got the cat, I got the bra. What do you do with these two things? You get the bra-ket, right? So let's see what happens if I do the bra-ket. Okay, so now, so I got a, let's find the inner product. Okay, so inner product is, well, I take the bra and then I ket this, so I got a bra-ket, right? So that means I need to do this multiply by this. So let's copy this over. Dx psi complex conjugate and then x, and then the bra was the original one. Okay, so this one is where you have to be careful, right? usually where I have two integrations in the same equation now. So I have two integration in the same equation. I need to make sure who is who. So I have two separate x. Okay, so I'm gonna put one of them to avoid confusion. Okay, so prime here. Okay, so this one is of x here and then another x, but these two are two different things. So later when you multiply, right, you should not confuse each other. So I put a prime in one of them. Okay, then I expand. Okay, so I'm gonna expand this. So expand this. Well, these are integration sign, and now you see why I like to put all the x in front, because yeah, it's very easy to organize everything, and then the rest of it we'll just arrange it here. So the psi bar x prime times psi without the bar and x, and then this is bra x prime ket x. Okay, so multiply, you get this. And then what was this? We mentioned this just now. This is the delta function, right? So what we're actually doing is I am integrate. So this is actually a double integral, right? So this is dx and then dx prime. So this is psi x prime and then psi x delta x prime minus x. Okay, and then let me integrate. I have two integrations, so let's do one of the integration. Okay, so let's integrate dx prime, right? So I will integrate this function as a function of x prime. So when I integrate this function, right, this will pick up the value where these two are equal. So it will make this equal to x. Okay, so integrate out one dx prime. So this one haven't integrate yet, but when I integrate the x prime, right, the x prime will change to x, right? And then so this is why like delta function is magic. So it just picks out the value to be the same as this x over here. So originally, just now I said there are two separate x's, two separate x, but when you use the delta function, it will just match them to be the same. Okay, so that is why, yeah, it's a magic. Delta function is something magic. Okay, and what is this? So it's the same function times the complex conjugate. So this is actually the absolute value square, right? So this is the absolute value square, and then this is psi. Okay, so if I want to be normalized, if my state psi is not is normalized, that means psi x must be equals to 1, which is to say that the wave function integrate psi equals to 1. Okay, so this is the condition that we encountered previously when it was a summation equals to 1, but when it was, and then now it takes the interpretation where the psi absolute value is the probability distribution, right? So later, I haven't shown you yet, but later the psi absolute value is going to be the probability function. So the probability function, the area under the function must be equal to 1. So the same story happens here, right? So in that, this is why we need to normalize the state. Okay. Sorry, why x prime ket is x? Actually, it's a choice. You can do it the other way around. It's like your personal choice. So it's, yeah. Is in, yeah, correct. Infinite dimensional Hilbert space. Yeah, so the, yes, so the values of x, each x form a basis. so it's infinite dimensional. Yes, continuous variable, yes. Discrete component, yeah, so for currently, no, not yet, no discrete component yet. So discrete component was what we did in the previous chapter lah. So now we have moved on to continuous. Okay. Although there are cases where the same state psi, right, the psi can describe an electron. Okay, so another thing I mentioned, was it, I don't know when I mentioned this, but an electron, right, so an electron is an electron. It is described by a state, but it depends on what you want to measure. So if you want to measure the position of the electron, then you get this continuous variable, right? We want to know where is the electron. But if you just want to measure the spin of the electron, then it's a two-dimensional Hilbert space. So you use the sigma z, you use the Stern-Gallup. So it's still the same object, right? It's the same particle, same electron, but it depends what question you want to answer. Where is the electron, or is the electron pointing up or pointing down? Right? So the same particle can, the same ket here can be expanded into an infinite basis, or the up-down basis, or some other basis. Okay. Mixed variable. Oh, that sounds like something complicated in statistics. So this is what happens in probability, is it? At least for us, no. Yeah, for us, no. At least for now lah, we focus on the position first. Wow. See, so I guess statistics is even harder than physics, harder than quantum mechanics, right? Yes, Zuri. So it's a normalized basis. Okay. I'm not used to starting the clock at 30, so I guess now it's been, yeah, so we should take a break now, right? So it's 5:28, 5:29, so let's take a 10 minutes break. And yeah, so we continue the story after this. And I believe, yeah, so someone wants to present. If there's anyone want to present, we can do the presentation also. Actually, yeah, me too, I'm also hungry. Yeah. Anyway, 10 minutes break. We come back and continue later. Continue. Okay. What question? So full screen. Hang on. Test. Okay, so just now I was telling you about how a state must be normalized, right? So what we have now is that it is the integral of psi squared. Okay, so this is what we call the normalization condition for the continuous variables. So normalization condition. Right, so to compare and contrast what we did for the discrete case, it was the inner product for a discrete, for a function in the discrete basis, it was the summation of the coefficient absolute square, and this must be equals to 1. So when we were talking about when discrete, right, this will take the interpretation of the probability. So it will be the same story here, right? So this one, this thing here, right, the absolute value of the wave function itself is going to be, well, I'll just call this px, and it is the probability distribution function. So write everything out. Probability distribution function. Okay, so yeah, in Dr. Gloria's class, I think it's called PDF, I think, right? Brightness. Okay, and it is the same way that you deal with the probability in your probability and stats course, or something similar, right? So you can use this to, yep.
Confirm with you, the big P of x, the maximum value, is it 1?
The maximum?
If you integrate it, yeah.
Oh, the integral will be 1.
Do you get 1?
Yes. Yeah, so yes, correct. I forgot this part. You mean this, right?
Okay, so if you integrate this function, you will get 1.
Yeah. So this is this thing square. Yeah, so the integral of p is 1.
Yeah, okay. Probability. Okay, we will discuss this later. I think it should be called probability density function.
Ah, okay.
We'll
I remember
discuss
PDF, but I forgot the what the D stands
yeah,
for.
we can discuss it later actually.
Okay, sorry.
Yeah.
The
Because,
stats lecturer scold me
if you use
already.
distribution function, it means something else.
Ah, I see.
But maybe in quantum mechanics, it means something else. That's why I will ask you later.
Oh, okay.
Okay.
Yeah, density. But okay, luckily for us, because you know, in physics we can avoid confusion with stats people. We'll just say psi square. Okay, so this thing square, and we will use this to calculate the probability. So for instance, right? Yeah, this another different terminology. In stats, it's called the expected value. Here we call the expectation value. And remember, we are dealing with position now. So if I want to calculate the expected value of position in the state psi, right? And then you have psi is equals to the integral over dx of psi x equals to x, right? So we got this situation here, and then my x operated on psi. Oh, hang on, I totally forgot. Zero wants to present, right? Yeah, I'm sorry, I forgot about that. Yeah, so okay, so let me finish this first, and then we can let you present. Hang on. So we got integral over dx. So the x operating on this is the x operating on all this thing here. So this thing operating x psi ket of x, and then the operator is operating on ket. So all these are scalar functions. You can ignore it and shift it away, and then is x operating on x. Okay, and x operating on x is equal to x, the ket x. So what we have here is the integral of, with respect to dx, and then is small x times the function of x, and then the ket x. Okay, so we got this now. And then if I want to find the expected value, means by the postulate of quantum mechanics, we need to do this, right? So we need to do this. So that means this is the bra of this thing. So I will to avoid confusion with this x, I call this x prime. So I got this thing is a function of x prime, and then the bra x prime over here, and then I multiply with respect to x integral x psi x, and then ket x, and then I expand the bracket, so I multiply everything out. The good thing about writing the dx in front is I can just shift everything here, and then the scalar function I write here, and then the bra x prime ket x, and then this is the delta function, right? So this is the first time you guys are seeing the delta function, right? So I write more steps, but in the future I might skip, because usually when you see this you can immediately jump to the next step, but if you're not used to it, I will show you the details, right? So I got the delta, let's say the delta x prime minus x, and then I integrate this with respect to x prime, right? So if I integrate with respect to x prime, the delta function is a magic function. It just turns this to make it the same as x. So this becomes dx x psi bar x psi x, and yeah, then the rest is gone, right? So what is this? This is just the absolute value. So this is the integral of x, and then psi x squared. Okay, so this is the formula to calculate the expectation or expected value of your position. Okay, so remember we are talking about quantum state here. Position of a particle, right? It is a probability. You don't know where it is before you observe it. You only know what are the chances of finding it here or there, and whenever there's a probability, you can find out what is the expected value or expectation value. And given a wave function, this is how you calculate the expected value. Okay, so you can do the same thing for the expected value of x squared, and I believe in probability this is called the second moment of the probability, right? So you can derive this in the same way. You should try it yourself. You will get the x squared and then psi squared. Okay, so if you want to calculate this thing square, the second moment of probability. Okay, so yeah, so Zhi wants to present. Do you want to?
Hello, sir.
Yes, hi.
Can I share my screen?
Yep, yeah, go ahead. Yeah, sorry, I forgot. Usually we present after the break. And you kind of see what we are doing, or what I'm doing with the tutorials. Initially we found the sigma z eigenvalues, and then in that question find the sigma y. So naturally you might want to find the sigma x, because those sigma x, sigma y, sigma z, right, these are going to be important operators in quantum mechanics. These are called the Pauli matrices. So I have not used the name here yet, because we were only talking about the Stern-Gallup, but later we'll realize that these three operators are going to be quite important. Okay. Oh, no lah, not n. So it's just the presentation component. So I guess luckily Kaheng no need to worry about presenting. Or Kaheng also can present if you want. That would be great. Okay. Momentum. So the next, I guess, if no one else wants to present, I shall present momentum and kinetic energy. Okay. So we have talked about the position, observable. Now let's discuss momentum. Okay. Oh, my term. Okay, so I'll read this later, but I should probably at least get started on this. Okay, so for momentum, okay, just now we talked about position. The next important thing is momentum. So for those of you taking theoretical mechanics, right, you will start to sense that position and momentum are two important quantities in physics, even in theoretical mechanics and also here in quantum mechanics. Right, so it seems to be position and momentum. It's not position and velocity, right? Momentum somehow is more fundamental. Okay, so let's try to understand this. So momentum of a particle, just like anything, it is an observable. So we expect it to have an operator. Okay, so I'm going to call this Hermitian operator for this observable, well, P, right, a natural name. And how do we describe the momentum of a particle using the quantum state, right? Because in Newtonian mechanics, P is mass times velocity. So this comes now we see a complicated situation right now, because our state now is ket psi, right? We have no idea what is the velocity of this object. So we cannot use this definition anymore. Okay, so we cannot use this to define the momentum. In fact, in theoretical mechanics, later you will learn about how to define the momentum. But for us, let me give you the answer straight away. Defined by what? Okay, so let's think about this. How should we define this? Well, it is an operator. So it's an operator. That means the operator should eat a state, right? And then it should spit out a new state or another state, right? Or shit out, if you prefer. So let's say the state I start with, since I'm talking about continuous variables, so let's just straight away use our position wave function. Okay, so let's say the state is described by this. Okay, so a state by then given a position wave function, then I could write this as the dx psi and then ket x, right? So this is my state that I'm talking about here. So this thing here is my state, representing my state, and the operator is supposed to eat this state and spit out another state. So what is the state that it spits out? I shall tell you the answer. It is given by the derivative of this function, and then I times h bar divided by I. So derivative of function is a function times a scalar function. You get a new function. So this will be a new state. Right? So that is the action of this momentum operator here. Okay. Let me fix the brightness. Okay, so I hope you know what this means. Maybe it's not very clear yet, because this is like, it's not very clear because why suddenly I say this. Okay, and the reason is because it will give us the correct value of the momentum of a particle later. Okay, so in other words, if this one is just like saying by words, right? But what to define this quantity mathematically, that means the operator acts on the state psi, and then I should get a new state, right? And then it is a new state whose wave function, new wave function, is is, I call this psi, phi is h bar partial psi partial x. Okay, so this is going to be a new state, right? So a new state, that means it will be given in terms of I will get a new state here. This is my new state after p acted, right? And the corresponding wave function is h bar over I partial psi partial x. So this is my new state where my function is this, right? My wave function is this. So in terms of the ket, it is going to be given by the integral over here. Okay, so the original state was right. So the original state was this, and then this momentum operator will eat this state and will spit out a new state given by this. Okay, does that make sense? Okay, so the position wave function, so the just to remind you, right, the position wave function of the new state is the new state is supposed to be some function x and then expanded in terms of this. So if I were to compare equation 1 and 2, right, the new wave function is given by h bar over I partial psi partial x. Okay, so given a wave function, I differentiate times h bar over I. This is my new wave function after my momentum operator acted on it, right? So for simplicity, we can write this as, we say the action of the operator P is h bar over I and then partial x. Okay, so this is a very common equation that you will see a lot in quantum mechanics textbook. This is my momentum operator. So this is what we call the momentum operator, right? And as you go to higher level problems in physics, right, this is the differentiation. This is a derivative. So this is a derivative before you put in the function. So this is one way to imagine that the differentiation is an operator, is an operation, right? So you take a function, you differentiate it, you get a new function, right? So the differentiation itself is an operator. Okay, So that is one way to view our Hilbert space, because now we are thinking about things in terms of functions as well, right? So an operator is to eat something and then we spit out something new. But right now, when we talk about position, my position wave function is a function. So the operator will eat something and it will spit out a new function, and this is like a operation. So that's why the derivative is called an operator, right? So take a simple example. Let's say my function is x squared, right? So if I differentiate this, I take a function and I spit out a new function. Okay, so this is an operator. Okay, so yeah, is your mind blown again, or is it something that you already know? I'm kind of not sure whether this is new to you or not. It's just like it's like taking something that you know already, but you're viewing it from a different perspective. So this is why I'm not sure whether it's comfortable to you guys or not. In any case, we can do some things about this. So I will start with this equation again. So I will, so another way to write everything that we have so far is that P acting on the state psi, right, is this P operating on, well, the state psi is expanded in terms of the wave function times the basis, and then P acting on this is the same as dx h bar over I, and then the psi dx, this thing. Okay, so now let's do so this was my new state 2. So we notice that we observe that from using equation 2, we got x. So if I close this with the bra x, right? So this is the same as equation 2. So if I close this with the bra x, I'm actually finding my wave function here. So if I do this on this side of the equation, right, what I have here is what I have here is basically closing this with the x. So now I have to be careful. This is x prime, right? And then this is h bar over I d psi x prime dx prime x prime, because these two are not the same, but eventually, because the delta function is magic, let's see what happens. Right. So d psi x prime dx prime, and then this one becomes the delta function, right? So this becomes the delta function x minus x prime, and then I integrate this with respect to x. So I got h bar over I. So if after I integrate everything with respect to x, it just picks out the value to be the same as the x here. This is the magic thing about the delta function, right? So I got x p psi. Okay. Now, let's do another magic trick again. Let's call this equation 3. Is everyone okay? Oh. Yeah, I know. So let's not stress Kahing. Yeah. We want, yeah. Kahing can relax. Because you already got a full workload, right? Yeah. So where were we just now? Yeah. Furthermore, I want to show you another thing, right? Yes, just now Zuri commented it looks like Schrodinger equation. Yes, Schrodinger equation is coming soon. Once we understand this, we will connect our Schrodinger equation from chapter 2. We will massage it until it looks like the Schrodinger equation that you have seen last time. But here, right, I will show you something here. Furthermore, remember that the psi of x. What is psi of x? Psi of x is what you get when you close your original state before acting P. with your x, right? So this is the definition of the wave function. The wave function. This is how you get the wave function in the first place, right? So that means if I look at this, so this is actually the, if I compare this equation, right, what is this saying is that the bra p psi is h bar over I d dx and then x psi. Okay, so now we notice that now I come to this stage again, then I notice this. Here both sides of the psi are arbitrary. So since psi is arbitrary, I can like cancel both sides of the equation, right? So that means what I have now is P, now P is like acting on the bra x here. This will give you a new bra, right? This is P is a Hermitian operator, so it can go left and it can go right. So what it means is I'm cancelling the psi, so this is an equation for a bra, right? P times this bra is the same as derivative of this bra. Okay, and then I got this result. I can do the Hermitian conjugate. I dagger the both sides, so I got px, and then the 1 over I dagger, so it get negative h bar over I d dx x. So I got another equation. I will call this equation 4. Right. So these are a few results that come out of defining the momentum. Okay. Any questions so far? Yeah, so I totally understand if you guys black out or get lost or anything, right? This is like totally new, right? We have never done anything like this in the previous courses, especially with this bra-ket and Hilbert spaces. So it will take time to digest, but trust me, this is, remember, right, this is going to feel like playing Tetris. So it's like you manipulating things like that, and the same thing works here. And also, I'm sure that the first time you play Tetris as a kid, you also don't really know what to do, right? It's only after you play a few times, then yeah, you know how to manipulate the thing, right? I swear, it's the same story that is happening here. Okay, so I got this a couple of things now. Now the question is this, okay? I got an operator P, and then I have defined how it acts on the eigenstates of X. So these are eigenstates of X. This is P. Then how about the eigenstates of P? So this is what we want to find now. Okay, so that means yeah, so I want to find the eigenstate of P. So that means I want to find some state that I act on it, it will just give me the same state again, and it will give me the eigenvalue. So since these are eigenstates of P, we'll just call this ket P, right? So I want to find what is P. Okay, so how do we do this? So we're going to use a couple of we're going to use a couple of magic tricks that we have already learned. So let's see. Okay, so now, right, the way to do this is I will use the trick that I did just now, which is to say that for no reason, I will just put the identity operator here. Okay, so I'm going to put the identity operator here, and I'm going to put the same identity operator here as well. And why did I do this? Because I want to use the completeness relation. So recall that the completeness relation for X is the integral of the ket bra, right? So this is what we call the inserting the identity. So if I do this, then I got this, and then I got this, ket bra close with p, and then this is just a number, so p integral dx ket bra and then p. Okay, so I operate the p into this ket, right? So p is a Hermitian operator, so it only eats ket. This becomes a number already, so it's not scared of p anymore here. So it's just this thing here. So this will eat this x here, but these are numbers, so let's keep this here, so nothing special is happening here. Okay, now this is the inner product between an eigenstate of x with an eigenstate of p. But anyway, we will worry about this later. What do we have here? This px, right? I have derived this equation over here, right? So using equation 4, what do we have here is p acting on x gives me a negative h bar over I, and then the derivative of x, and then xp, right? And then on this side, is p dx, and then I got x, and then xp. Okay, so now I come to this equation. Now let's look at x and p. Okay, so what is x and p? Well, p is an eigenstate, and then closing it with x. So closing it with x will give me the position wave function, right? So in other words, xp, it will give me a wave function that is the wave function of the eigenstate, the position wave function for the eigenstate. Right, this is the definition of position wave function, right? I got a state, I don't know what this is yet, but what I do know is if I close this with the x, I will get the position wave function. That is how we define the coefficient of my basis, right? So what is happening here is, well, what is happening here is I got the integral dx, okay, and then this is h bar over I, and then I am operating a derivative. So now this derivative, let me swap places a bit. So this is x and p, and then this is the ket x, because the derivative is now what it's doing is it is acting on functions, right? And then on the right hand side is now is a dx, and then this is my xp, and then this is ket x, and then I said that this is the position wave function. So let me change this into the position wave function. This is the derivative of psi with respect to x, and then this is ket x, and then this is dx, and then psi x, and then x. Okay, so again I will remove the integral, because comparing left hand side and right hand side, right, I conclude that I can kind of cancel the ket x on both sides. So basically what I have here is dp dx is equals to psi p. Okay, in other words, I got the psi dx is equals to negative I over h bar psi p. Wait, hang on a second. Why do I get a minus sign? Oh, I made a mistake. Hang on. There should not be a minus sign here. Okay, so yeah, to avoid confusion, let me fix this. So the P acting on dx x p x is equals to this, right? So I'm not using equation 4. Yeah, I made a mistake. Then otherwise there's a wrong minus sign. I got this over here. Okay. Yeah, so don't worry about this. I will clarify again later. I will explain the steps again later, but since we got this differential equation, we should solve this differential equation, right? So this is a differential equation with a solution what? Well, everyone knows this differential equation, right? This is just the derivative and then psi. So the answer is the exponential. Okay, so I got a constant e to the power of oh, another mistake I forgot is I left out a p here. So there's a p here. I forgot the p. Yeah, sorry, I keep confusing myself today. There's a p, and then there's a p here. So in other words, this is ipx over h bar. Okay, and this is a constant. So to determine the constant, we normalize this, right? So normalizing psi px will fix the constant. And what did we say about normalization? Well, to get the normalization, right, the eigenstates must be normalized, which is to say that p inner product with p must be equal to the delta function but with p, right? So let's try to work this out to make sure whether this is normalized or not. Okay, so yeah, so the p vector, remember what was p, right? So the p was, let me write here to remind you guys, this is the dx, and then this is the eigenstate in terms of x, right? So if I take the bra, it's going to be this bra, okay, psi p x prime complex conjugate, and then times with the eigenstate p again, but without the primes. Okay, so that means what we have here is integral dx prime. Okay, and then I got this times this, so we got this bar px prime, and then this x here, and then x prime with x. So this is my delta function, right? So if I integrate the x prime here using the magic of the delta function, it will change this into my x. So I got this thing here, and then this is just psi bar p x psi p x. And actually, what is psi p x? So psi is what we got here. So this is actually the integral with respect to dx of a bar times a e to the power of I forgot to prime the p as well, right? So it's the minus I p x over h bar e to the power of complex conjugate I p prime p x over h bar. So this will becomes integral a square, and then this becomes ip minus p prime x over h bar. Okay, so I come to this equation, but remember what I want to say, that I want this to be orthonormal. Okay, so if I want this to be orthonormal, that means this thing must be equals to what? So this thing must be equals to the delta function, right? So this must be equals to p minus p prime. And in fact, if you work this out, and this was also we can almost get the the value of the delta function here already, right? So you got this thing over here. Remember at the start, how did we define the delta function? So the delta function was defined to be the integral of the constant, then this minus this prime, right? So we got this. So if I work out this integral, right, this is going to be well, if you work out this integral, it's going to be h bar times 2 pi delta p minus p prime. Okay, so this is going to be my the delta function over here. So if I were to make it normalized, right, if I want to make this equals to this, then my constant a should cancel with this, make it equals to 1. So I shall choose a to be 1 over square root of 2 pi h bar. Okay, then we have p equals to delta p prime minus p, which is also normal. Okay, so finally we have found the eigenstates. In other words, the eigenstates of position momentum wave function is given by 1 over 2 pi h bar, right? And what we got was, we have determined the constant a, and then the function is e to the power of ipx over h bar, and it is the same as xp. Okay, so this relation here is going to be important in quantum mechanics as well. This is what we call the xp transformation function. Okay, so this is called the xp transformation function. Okay, so yeah, wow, we have spent 3 pages on this. So 6, 7, 8, 9. Yeah, I understand if I might be confused because I made some mistake myself, so it might be throwing people off a little bit, but maybe I will come back to this again in the future. But for now, so I will come back again, maybe if there's time we'll come back again in the future, but for now, right, the main point of this exercise is to derive this result, and this result is important. It's called the xp transformation function, and it is kind of like the origin of the Fourier transform I mentioned last time. This is one way to see is that this one is like changing from p and eigenstate of p and expressing this as a function of x. Okay, so p and x are complementary variables, and this relation is going to be very useful to derive a lot of results in connecting position and momentum. Okay, let's see if you have any questions. Yes, the p is the eigenvalue. In fact, that is what I want to do next. Okay, so let's check. Oh, okay, yes. Yeah, I was talking a bit just now, but I wasn't sharing screen, so I will come back to this later. Now that I'm sharing screen, so I can write down what I wanted to say just now. Okay, so hang on. So, but I guess the question to address now is to check, right? Just now I claimed that the state P is an eigenstate, right? Okay, so let me manipulate this and show you like whether this is really an eigenstate or not. Okay, so this state P, again I will use the trick that we have been using a lot. Okay, just to show you and just as a practice, for no reason I times the identity operator, and this identity operator is the completeness relation. So x over here and p. Okay, and we have just derived the formula for this. So now I know that this is the integral. This expression is 1 over 2 pi h bar, right? And then I got e to the power ipx over h bar, and then the ket x over here. Okay, so I got this now, and then I claim that this is an eigenstate. So what's the eigenstate? If I act P on this, do I still get the eigenvalue P? So let's find out. Okay, so acting P on this state is, well, let me push the constant in front first. And then what does P do is P is h bar over I d dx, right? It is an operator. So this is h bar over I. Okay, so this h bar over I d dx. And then what am I differentiating is e to the power of ipx over h bar and then times the ket x over here. Okay, so let's see what happens if I work out the differentiation. Okay, so this will become, let's keep the h bar over I. So if I differentiate this, differentiate with respect to x, I got ip over h bar come down, and then e to the ipx over h bar x. Okay, so the I cancel with I, the h bar cancel with h bar. There's a p here, so let me move the p here just to make it look really like an eigenvalue, and then I move this constant back inside. And then you see that this was the same as the beginning, right? It's the same as the beginning. So this whole thing is back to P again. So yes, we have checked that the P operator and the P eigenstate, they are all, this P is the eigenstate of the operator P, and this small p is really the eigenvalue. Okay, so yeah, any questions so far? Okay, so I guess that's the end of the class. Again, I'm sorry, I'm not used to ending the class at the 30 minutes, so we should end by now. But if you want to exit and have dinner, go ahead. Let me just leave the recording running to answer your question here about Zhi's presentation. And you can check the video later lah. So let me talk about this for the last few minutes, right? Yeah, feel free to exit the meeting and watch the video later. So just now, right? So just now is, yeah, we do not observe anything on the Z screen, but what is happening here is that Zhi find the eigenvalues to be, let's call this E1, right? And then sigma y eigenvalue of E2, and then the E1 found was what was it, I and 1, right? Is it I and 1? So let's normalize this. So this is 1 over square root 2, this thing. Okay, this is the eigenvalue 1, am I right? And then this is the eigenvalue of negative 1. So let me yeah, let's normalize this. 1 over root 2 and then minus I 1. I think this eigenvalue is negative 1. I think it doesn't matter. So let's say if I pass the spin up, right? So what was my spin up? The spin up was 1, 0. Okay. So what is 1, 0? We can actually express this in terms of the origin, the spin up and spin down. So let us look at this equation. Okay. So this is 1 over root 2 I1. Okay. So 1 over root 2 I1 is actually I over root 2 1, 0 plus 1 over root 2 0, 1. Okay. So this is actually I over root 2 spin up plus 1 over root 2 spin down. Okay. So you do the same thing here, 1 over root 2 negative I1. So you realize that this is negative I over root 2 spin up plus 1 over root 2 spin down. Why did I? No need bracket. Okay. So I can actually express my spin up and down in terms of this new basis. So what was this? This was E1. This was E2, right? So let us take equation 1 minus equation 2. So if I take equation 1 minus equation 2, I get E1 minus E2. So this becomes I over root 2 I over root 2 spin up plus 0. So this becomes root 2. So the spin up is actually 1 over root 2 I E1 minus E2, right? And then so what you have here is minus I. So let me bring the I on top. E2 minus E1. Okay. So what you have here is now I got the sigma y operator, right? So this is sigma y, and then what is happening here is I will split this into the two eigenstates of sigma y. So one of them is the eigenstate E2, the other one is the eigenstate E1, right? So yes, nothing is observed on the z-axis, but this is observed on the y-axis over here, right? So the state spin up is split into these two eigenstates. Okay, does that make sense? So the idea is that, okay, if this is spin up in the z direction, right, and if you measure sigma z, then there's nothing here, you only get the spin up coming out, right? But now you are measuring sigma y. So sigma y is sigma y, the eigenstate is E1 and E2. So if you measure this, then you get the E1 eigenstate one way, and then the second eigenstate the other way, right? Okay. Yes, correct. Yeah, in the z direction. So yeah, on the y direction, sorry. Okay, so yeah, yeah, I guess that's all for today. Let me stop the recording. Already dragged